Okay. So y is equivalence class non-empty. Class A is not equal to y. So we begin the proof. So we have. So what is the definition of equivalence class? Equivalence class of X is the set of all those y in A such that y comma X belongs to R. Okay. Means related to X. Okay. Or it's the same way X y related to R belongs to R because R is a equivalence relation, so it is symmetric. Okay. So we have this definition. So number one is so we start with an arbitrary element in capital A. Okay. Let A belongs to A, be any element. Be any element. Okay. So I have to show that equivalence class of A is non-empty. Means I have to find at least one element inside equivalence class of A. So can you find some element? If A is inside A, capital A, then can you find some element inside equivalence class of A? What is equivalence class of A? Equivalence class of A is the set of all those X in A such that X is related to A. So we have. So can you find one element which is related to A? This small A. A itself, because this relation R is equivalence relation, so it is reflexive. Okay, reflexive. So since R is reflexive, so A comma A belongs to R. So by definition of this, A belongs to equivalence class of A. Okay. So always equivalence class of A is non-empty. Most obvious element in equivalence class of A is A itself. Okay. So therefore equivalence class of A is a non-empty set. Okay. They are never empty. Whatever be the relation, they are never empty. Right. So equivalence class of A not equal to Y. So always remember that A belongs to equivalence class of A. Okay. Whatever be the relation. Next is if A belongs to equivalence class of B, then AB is related. Okay. So it's a two-way implication. Number two is let us start with this. So this is obvious. Let A belongs to equivalence class of B. Okay. So then by definition, equivalence class of B te kara thakbo jara B er sathe related. Okay. So by definition, AB belongs to R. Okay. So if A is in equivalence class of B, it follows from definition that B is in R. Okay. And what did I write? This is not required as a property itself. Okay, this follows from definition only. No? AB is related, that means A is in equivalence class of B. Okay, so it follows from definition. So this is conversely if AB belongs to R, okay, then A belongs to equivalence class of B. Okay. So this is obvious. So no need to do anything about it. Another is number 3 property. Number 3 property is if class A and class B are equal, then A and B are related. So first let class A equal to class B. If the classes are equal, then A and B are related. Okay. So let class A equal to class B. So we have by first result, A belongs to equivalence class of B. Okay. We know that A belongs to equivalence class of B. Okay. So this will imply what? But equivalence class of A and equivalence class of B are same. Okay. So this will imply that A belongs to equivalence class of B. Okay. And what does this mean? Means that AB is in R. Okay. So this is also there. So it's very simple. Class A and class B are equal, and by the first result we have A is in equivalence class of A. Okay. So we can replace equivalence class of A by equivalence class of B, and then by definition it follows that AB is related. Okay. Right? Then the other way. Okay. If AB is inside R, then class A and class B will be equal. Okay. That one. So conversely, let AB belongs to R. Okay. A and B belong to R. Then I have to show that class A and class B are equal. Okay. So equivalence class is actually a set. Okay. So when are two sets said to be equal? If each is a subset of the other. Okay. So class A is a subset of class B. Class B is a subset of class A. You have to show this thing. Okay. So let X belongs to equivalence class of A. Be any element. Okay. So what does this mean? This will mean that X comma A belongs to R. Okay. If X is an equivalent class of A, this will mean that X A are related. Okay. But now X comma A and A comma B belong to R. We have supposed that AB is in R. Okay. And from here I have got that XA is in R. Okay. So that means what do I have? I have XA and AB. They are inside R. Then I can use what property? Transitive. I can use the transitive property of R. From there I can conclude that XB belongs to R. Okay. Now this and this belongs to R, and R is transitive. Okay. R is an equivalence relation, so it's transitive. Okay. So we can conclude that XB belongs to R. So from here it will follow that X belongs to equivalence class of B. Okay. X belongs to equivalence class of B. So every element of class A is inside class B. Okay. Every element of class A is in class B. That means class A is a subset of class B. Okay. So therefore class A, this is a subset of class B. Okay. So one part I have shown. The other part is I have to show class B is a subset of class A. Okay. That's good. So how to show that? So we will take an arbitrary element from class B. Okay. Be any element. Okay. So this will imply that X comma B belongs to R. Okay. X comma B belongs to R. What I have to show? I have to show that X comma A also belongs to R. Okay. So how can I show that? So we also have AB belongs to R. No? This is in R. Okay, but for transitive, what do I need? XB and then B starting with B. Okay. So we have AB belongs to R, and R is what? R is, I can use the symmetric property. Okay. Symmetric. So BA is also in R. Okay. Our supposition is AB is in R, but R is symmetric. So BA is also in R. Okay. So I can combine these two now. Therefore, by transitive property, by transitivity of R, we have X comma XB BA. Okay. So XA will be in R. So this means X belongs to equivalence class of A. Okay. So ultimately, what is our conclusion? It is class B is a subset of class A. Okay. So you can name it 1. This one you can name it as 2. So from 1 and 2, it follows that class A and class B are equal. So from 1 and 2, 1 and 2, class A equal to class B. Okay. Okay, so both things I have shown. Class A equal to class B implies and is implied by A B belongs to R. Okay. So whenever A and B are related, their equivalence classes will be same, identical. Okay. Okay. The next one is any two equivalence classes are either disjoint or identical. That is what I will show. That is what I have to show is this. Number 4. So let A comma B belongs to capital A. B any element. B any elements. So what I have to show? I have to show that either class A intersection class B is phi, or class A is equal to any two equivalence classes are either disjoint, okay, or they are identical, okay, but not both, not both. Nothing else. They cannot have intersection. Okay. Either they are phi. If they are not phi, then class A should be equal to class B. Okay. If they have something in common, then they have everything in common. Okay. If কিছু একটা common থাকে, then everything is common between them. Okay. So they cannot. So what is the proof? Proof is this. So if this happens already, we have selected any two elements. So if we find that they are disjoint, then there is nothing to discuss. Okay. So we will write these things this way. If class A intersection class B is phi, then there is nothing to prove. Okay. Nothing to prove. Means our job is done. Okay. Either class A intersection class B is phi or this side. So if this happens, so there is nothing to do. So let class A intersection class B is not equal to phi. Let class A intersection class B not equal to phi. Okay. So it is non-empty. That means what? It will have some element. এখানে একটা এলিমেন্ট থাকবো, okay, it will have some element. So let class A intersection class B not equal to phi, then there exists this symbol is called there exists some element C inside class A intersection class B. Okay. Then there exists some element C inside class A intersection class B. So this element belongs to class A also, it belongs to class B also.
Sir, class A and class B intersection which element is any element upon ordered pair.
No. Class A doesn't contain ordered pairs. Ordered pairs relation contains ordered pairs. Class A contains only elements. Okay. Class A contains all those elements which are related to A. Okay, which satisfy X A belongs to R. So it will have only elements. Okay. All elements of A. So there exists C in class A intersection class B. So C belongs to class A and C also belongs to class B. Okay. C class A মধ্যেও থাকবো, class B মধ্যেও থাকবো. Okay, because it belongs to the intersection. Okay. So from there you can write C belongs to class A means what? CA belongs to R, and C belongs to class B means CB belongs to R. Okay. C belongs to class B means CB belongs to R. Okay. So from here I can write R is an equivalence relation. So I can change this order. So AC belongs to R and CB belongs to R. Okay. So I want to apply the transitive property. Since R is symmetric. Because R is symmetric, I have changed this. It I changed. Next, I can apply the transitive property. AC is in R and CB is in R. So from here I can write A comma B. This is in R. Okay. And already we have shown whenever AB is in R, this will imply that class A is equal to class B. Okay. Right? Or you can show it separately. Okay. So just let me write, then show class A equal to class B. Already we have shown the same way you try to show. Okay. Means if it comes in exam as a separate question, okay, you do the complete part. Okay. AB belongs to R. After that, you take any element from A, show that A is a subset of class A is a subset of class B. Take any element from B and show that class B is a subset of class A. Okay. Do that part. Okay. So I am leaving it here. Then show that this. Okay. You can keep some gap and complete it. Same system. With the number 3 the same system. Okay. So we have shown that any two equivalence classes are either disjoint or they are identical. So your equivalence classes, they cannot be something like this. Okay, this and this. This cannot be equivalence classes because they have something in common, something in uncommon. Okay, these two cannot be equivalence classes, but these two can be equivalence classes. Okay, separate. Okay, either disjoint or they are same. Okay. Okay. Next is partition of a set. What do you mean by partition? Partition. You try some problems later. Just try to some exercise you write. You try it at home. Let capital. Let R be the set of real numbers. Let R this R. Bold R. Let R be the set of real numbers. You write this question. Let R be the set of real numbers. Stop. Define a relation. This similarity symbol. This on R as A related to B if and only if A minus B is an integer. A related to B if and only if A minus B is an integer. Show that the relation is equivalence. Show that the relation is equivalence relation. A and B are related if A minus B is an integer. Full stop. Describe the equivalence classes. Describe the equivalence classes under this relation. Describe the equivalence classes under this relation. Full stop. Where you try this later. Another exercise. Let Z be the set of integers. Let Z be the Z. This Z. Let Z be the set of integers.
Next question.
Next, another question. Let Z be the set of integers. Define a relation R. Define a relation R on Z. Define a relation R on Z. on Z as A comma B belongs to R if and only if ordered pair AB, A comma B belongs to R. No, ordered pair. AB belongs to R. A comma B belongs to R. This way. A comma B belongs to R. Okay, define a relation R. A comma B belongs to R if and only if A into B greater than or equal to 0. A into B greater than or equal to 0. First of is R an equivalence relation? Is R an equivalence relation? A comma B belongs to R if and only A into B, AB at A, AB greater than or equal to 0. AB belongs to R if and only AB greater than 0. Is R an equivalence relation? Okay, another question to write. Let Z be the set of integers. So define a relation R on Z. Define a relation R on Z as relation R on Z as A comma B belongs to R if and only if A plus B is even. A comma B belongs to R if and only if A plus B is even. Okay, is even. A plus B is even. Okay. Full stop. Prove that R is an equivalence relation. Prove that R is an equivalence relation. Full stop. Also find. Also determine the equivalence classes under this relation. Also determine the equivalence classes under this relation. Okay. So under this relation, AB is related, A and B are related if A plus B is even. Okay. And AB is related. Okay, so next thing is this partition of a set. Partition of a set. Okay, so just see one example. Suppose your set is 1, 2, 3, and I write subsets like say S1, I write it as 1, 2. S2 I write as 3 and S3 I write it as. So these subsets they are mutually disjoint. Okay, means you take any two subsets, take the intersection, they are disjoint. Okay, so these are called mutually disjoint. Okay, a collection of subsets is said to be mutually disjoint if the intersection of any two of them is always empty. Okay. So S1 intersection S2 is empty. Pi. There is no intersection. S2 intersection S3 there is also empty. Okay. S1 intersection S3 there is also empty. Okay. So these are mutually disjoint. But what is their union? S1 union S2 union S3. What is this? This is the whole set. Okay. So this will be called a partition of the set 1, 2, 3. Okay. So suppose the set 1, 2, 3, 4 is this 1, 2, 3, 4. So we have partitioned it into three parts. Okay, this part is S1, this part is S2, this part is S3. Okay, there is the partition. There is nothing common between the partitions. Okay, and none of the partitions are empty. Okay, it cannot be something like this. It cannot be something like this. Okay, you cannot take union with phi. Union phi with S1 union S2 union S3 union phi. Then also it's A. But okay, but this will not be a partition because one of the members is empty. Okay, so that is not a partition. So each member or each subset should be non-empty. Okay. So what is a partition? Partition is a collection of non-empty subsets of a set which are mutually disjoint, and their union is the whole set. Okay, union is the whole set. Okay. So we'll write this here. Partition of a set. Just write this part. A partition of a set. A partition of a set, capital S. A partition of a set, capital S, is a partition of a set, capital S, is a collection P. Okay, so let us write it this as P of non-empty subsets of S. Okay. Subsets of S that satisfy number one. So two properties are there. One property is they are mutually disjoint. Okay. So we can write that as this. Say A intersection B equal to phi for all A, B inside P. Okay. If you take two sets from P, okay, so P is a collection of non-empty subsets of S. Okay. So A intersection B is phi for all A, B inside. Okay. That is the sets in P are mutually disjoint. Okay. Mutually disjoint. Okay. They are mutually disjoint. Okay. And then number two is the union of all these sets is the whole set. Okay. So S is the union of capital A, so that A belongs to P. Okay. So this is another symbol. I do not know how many sets are there in P. Okay. It may contain infinitely many sets. Okay. So I cannot write something like A1 union A2 union A3. Okay, we cannot write things like that. This is the symbol. Means whatever sets are there in P, you take the union of all those sets. Okay. So union of A, where what is this A? A is a member of this collection P. Okay. So it's union of A belongs to P. Okay. So that is union of all sets. Union of all sets in P is S. Okay. So in language we can say this. Union of all sets in P is S. Okay. So any collection of non-empty subsets of S which satisfies this is called a partition of the set. Okay. So for example, say A equal to, or say S equal to set 1, 2, 3, 4. Okay. And I take P as the collection of subsets. Okay. 1, 2, then singleton 3, singleton 4. Okay. This is a partition. Okay. This collection, so it is a collection of subsets. Okay. So the subsets are mutually disjoint. There is nothing common between any two of them. Okay. These are now nothing common. Take this two, nothing common. Okay. Take that two, nothing common. Okay. Then say this is a partition of this. Another partition, say you can think of singleton 1, singleton 2, singleton 3, okay, singleton 4. This This is also a partition of S. Partition. Their union is S. Okay. So there is no restriction which subsets you can take. Right. So several ways you can take this partitions. But say P equal to 1, 2, 3, 4, comma 5. Okay, this is not a partition. Is not a partition. Okay, it is not a partition of S. Why? Because one of the members here is empty. Okay, that is not allowed. None of the members can be empty. So this is not a partition of S. Right? Similarly, this is also not a partition. So P equal to, I write 1, 2, 3, and then I write 3, 4. Okay. Their union is the whole set. That's not a problem. But this is not a partition. Okay, it is not a partition of S. Why? Because their intersection is 3, singleton 3. Okay, so that is not allowed. They cannot have non-empty intersection. So intersection should be 5. This is not a partition of this. As 1, 2, 3 intersection with 3, 4 is not equal to 5. This is not a partition of S as 5 belongs to P. Okay, 5 cannot belong to P. Right? P should be a collection of non-empty subsets. Yeah. So some more examples. So if I take a infinite set, then you find out some partitions. Say I take Z. Okay, let us consider set Z. Okay. So write some partitions of Z. Some partitions of Z are some partitions of Z are. Okay. So tell me some partitions of Z. P equal to. Tell me some collection of subsets which make it a partition. Z, set of integers.
Set of natural numbers.
Set of natural numbers.
0.
Okay. N. What is
0.
0 and what?
Negative numbers.
Negative. Yes. We have to include the negative numbers. Okay. Say minus n. Minus n is something like where minus n is equal to set of minus n such that n belongs to natural number. Okay. So this becomes a partition. There is nothing common between n and singleton 0. N is the set of natural numbers. Integers से क्या ऐसे? It is only integers 0, plus minus 1, plus minus 2, plus minus 3. Okay. All these are integers. So we can partition it this way. We take all natural numbers here. We take all negative natural numbers there and singleton 0 separately. Okay. This is a partition. Any other partition? Another partition. This is a partition. This is a partition of Z. Okay. Some more partitions of Z.
Set of whole numbers. Set of whole numbers and minus.
Set of whole numbers, including 0. Okay.
Yeah.
So, n union 0, comma with that minus n. This is also a partition. Okay. So here zeros are included. 0 is included with this. Okay. Another partition. This is also a partition. This is a partition. Partition of Z. Okay. Another. So this is P1. This is P2. P3. Okay. Another partition. We have done something in the earlier class also. Another partition of Z. It is in doubt how we can separate. Yeah. Just I have to write some mutually disjoint subsets whose union is there. Okay. Try. T3, T4, T5, lots of infinitely many partitions you can make. What is that? Karo try karo, try karo.
Set of even numbers is not good.
Set of even numbers. R set of odd numbers. Yeah, this is another one. Okay. If I write T is the set of even numbers, okay. Even integers, okay. Say even integers. Even integers. Okay. So this is one. And together with that, let me write something like O, okay, which is the set of odd integers. Okay. So we have separated odd and even integers. That is also a partition. Okay. Right. There is nothing common between odd and even. Okay. There cannot be any number which is both or even or odd. As an even number. Both even and odd. Which number is there? What about 0? 0.
Sir, 1 1
0 is what type of number? Odd or even?
even
0 is an even number. Okay. 0 is not odd. 0 is an even number. Any number which is divisible by 2. Okay. It's even. So there is no number which is both even and odd. Okay. There cannot be such number. So this is also a partition. Their union is Z. Okay. Another partition. Till now we have done with only finite collection of subsets. Tell me an infinite collection of subsets. Onek gulo infinite. Tell me a partition which has infinitely many this members here. These are only finite, na? As sets they are infinite, but this partition has finitely many members. So suppose here there are 2 members, here there are 2 members, there were 3 members. Tell me a partition which has infinitely many members here. Onek class. What is that? Try to think. Infinitely many members are there. What sort of partition? One example already I have done with finite sets. Okay, you think of something similar with n. Okay. Think of a partition on n. Partition on n having infinitely many members. Infinitely many members. So you write a partition on n on the set of natural numbers such that there are infinitely many members in the partition. Okay, and their union is n. And they are disjoint equivalent, mutually disjoint equivalent. Okay. Think, try to think. I have to separate this set of integers into infinitely many parts. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So how can I do that? Infinitely many members. You have to take infinitely many subsets. Okay, how will you take?
roster method के represent.
Roster set builder form दिया और represent करते हो. Just think of something. Okay, roster की शब्द को. What is that? Or what are those? Think. Try to think. How can we separate n into parts? Okay, another part. What should I take here? And I have to take something here, so that they are all disjoint, and their union is the whole set n. What is that? एकदम simple. तो हम तो लिखे ही दिले इसी. What? Think for some time. Try. Their union is n. Try to write some subsets of n which are equally disjoint, infinitely many subsets. Okay. And their union is n. Think. What is that? Right, isn't it? Yeah, that's what I am saying. So the most obvious is this. तो हम तो लिखे ही सब अलग-अलग each one is a subset. Singleton 1, singleton 2, singleton 3, singleton 4. So how will you write this? This is in roster form. How will you write this in tabular form? This is the collection of all singleton n such that n belongs to this is the collection of all singleton subsets of n. Okay, very simple. So this is a partition which there is nothing common between them because each of them is a different natural number. Okay. And their union, if you take the union of all singleton sets of a set, then you get the set itself. So this is one. So given any infinite set, you can always take this partition. Okay. Singletons always partitions. Okay. Arakta barwaili. What is the idea? Another one. Try. Now you can find out many over there. What is that? Arakta bolos na? 1, 2. Double put 1, 2, 3, 4, 5, 6. Okay, like that. So there are many partitions. So how will you write this? You can write this one as set of n comma n plus 1 so that n belongs to natural numbers. Isn't it? No, incorrect. If I write it this way, is it correct or incorrect? This writing roster form is correct, but the set builder form is incorrect because if you start with n equal to 1, so you will get 1, 2. Next is 2. So 2, 3 again. Set builder form is incorrect. So I have to correct it. So what I have to take? N belongs to n is odd. Okay. If I take this 1, 2, so 3, 4, and 5, 6. Okay. Similarly, you take 1, 2, 3, 4, 5, 6. Okay. So many of them. Lots of partitions. So is the power set of a set a partition? Can the power set be regarded as a partition? Power set is also a collection of sets. No? Power set of a set is the set of all subsets. So is it a partition of the set? Why? Not disjoint. The better argument is phi belongs to power set. So one of them is empty. Okay. So that is good. Say for this singleton 1, if the set is singleton 1, okay, the power set here, everything is disjoint. They are disjoint. Okay, so disjoint argument is not working here. The argument that works here is one of them is empty. Okay, so empty set cannot be there in the world. Okay, so that's why power set is not a partition. Right. So we will take one theorem here. It is this is called the fundamental theorem of equivalence relations. Fundamental theorem of equivalence relations. Equivalence relations. So what is that? Let me state it from this book. The equivalence classes of an equivalence relation. Equivalence relation on a set capital S constitute a partition of S. Okay, so if you take all equivalent classes, okay, then you will get a partition of the set S. Okay. So on a set S constitute a partition of S. Okay, partition of S. Conversely,